I will, if it's okay, I'll take the honor of actually having a chance to introduce Elisabeth. So today we have Elisabeth Krause from University of Arizona. She did her PhD at California Institute of Technology in 2017. After being a postdoc at UPenn and also at Stanford and also at Caltech, she has become assistant professor in University of Arizona in 2018. She actually won a number of awards, IUPAP Astrophysics Young Scientist Award in 2018, DOE Career Award in 2019, and also APS Maria Gepper Mayer Award in 2020. She has been one of the leading experts in using large-scale structure and optical and a variety of cosmological survey that's listed here. She's a member of DES, LSST desk, and also the Roman collaborations. And she is theoretically oriented, I would say experimentalist, who has been doing a variety of work in the area of cosmological surveys and the area of big data. So today she will tell us about the large-scale structure cosmology in the systematic limited regime. So welcome, Elisabeth, and we're looking forward to your talk.
Thank you very much, Daisuke, for the spontaneous introduction, and thank you all for showing up. It's great to visit, at least virtually. So let me get started, and please feel free to interrupt with questions anytime. So I speak here today as an observational cosmologist, which means that I want to talk about the process of determining mainly 6 parameters describing our universe. We want to measure the age of the universe, the geometry of space, the density of atoms, the density of matter, the amplitude of fluctuations in the universe, and the scale dependence of these fluctuations. Of course, the details are not quite as simple, or we wouldn't exist, we wouldn't discuss this. But this basically is our vanilla lambda CDM model. Within this model, things then, as you probably know, get weird very quickly, in that ordinary matter, as we know, it makes up only about 5% of the energy budget today. Another 25% is in dark matter, where we have some hope of making progress in the lab. And the remaining 70% have been termed dark energy. This really is just a name for the phenomenon that the expansion of the universe appears to accelerate, as first measured by supernova in 1998. However, while we've given it a name, we really don't understand it yet. In the simplest model, a cosmological constant described by an equation of state of -1, observations in theory would disagree on the magnitude of that constant by 40 to 120 orders of magnitude, depending on how you count. In the next slightly more complicated model, it could be a dynamic scalar field, where that equation of state then picks up a time dependence. Or we could be witnessing a breakdown of GR. Suha Gürsey has joked that since the discovery of dark energy, there has been a different model on the archive every day. So that is a difficult position for data analysts to be in, because we can't go through and develop detailed modeling, confront them each with our data. So that means that for now, our main approach is to stress test the lambda CDM model. And we do so by asking whether data from the early and late universe are fit by the same parameters, whether measurements of the background evolution and dynamics, that is growth of structure, agree. And if we're going to measure one parameter about dark energy beyond its abundance, then we want to see whether its equation of state changes as space expands. In the early 2000s, there was this beautiful Concordance Cosmology, where we had measurements from the cosmic microwave background, shown in orange on the plot on the right-hand side, that shows constraints on matter density versus dark energy density, and measuring the angular scale of the sound horizon in the early universe, and telling us that the universe is spatially mainly very close to flat. Then we have baryonic acoustic oscillations, as shown in green. That is the angular scale of the sound horizon imprinted in the late time galaxy distribution, largely providing a constraint on the matter density. And in blue, supernovae, our standard ruler, our standard candle, measuring the expansion history of the universe. these three measurements beautifully agree, bringing us to concordance cosmology and the statement that dark energy makes up about 70% of the energy budget. Now in the 2020s, as we've really zoomed in on this lambda CDM model, trying to see whether it holds up, there are first cracks in that our measurements of the expansion rate or Hubble parameter are in significant tension between early and late universe physics, as shown here in this plot, showing from a summary paper showing constraints on the Hubble parameter from early universe physics measurements, that's from the cosmic microwave background, or early universe physics imprinted in the late-time galaxy distribution, compared to various late-time measurements. The significance of this tension currently keeps going up and up. It is over the 5 sigma threshold, and definitely a big puzzle in lambda CDM cosmology right now. Then the other aspect is the amplitude of structure growth, as summarized in the plot on the right, showing you S8, a parameter for the clumpiness of the universe versus meta density, comparing various late-time measurements of the meta distribution from relensing in yellow, purple, and gray against the measurement from Planck cosmic microwave background. Whether this is a tension or not is definitely under debate. It is not won yet by particle physics standards, but definitely another very interesting part of the puzzle. So our goal now is to shrink these error bars. And in order to do so, let me already basically give you the summary of my talk. In some sense, that is a preview of cosmology analyses later this decade, where I believe we'll have about 5% of parameters that we understand very well. Those are then our cosmology parameters. And the other 95% will be related to systematics modeling, both in terms of observational systematics and astrophysical systematics. And these will generally be known unknowns, where we can really do our homework beforehand and optimize analyses, and previously unknown unknowns that we can only uncover and make sense of once data arrives. But I want to talk you through the work program that we can carry out right now to make sure that there are as few unknown unknowns as possible once we come to data analysis, so that we can turn galaxies into physics constraints as quickly as possible, and hopefully with as few unpleasant surprises as needed. So for that, let me give you some context of photometric dark energy surveys, where I'm showing different generations of surveys here, ordered by their start or end date on the x-axis, and then I visualize them in terms of survey area on the sky by the blue squares. And the small red dots indicate the observed galaxy density in terms of galaxies per square arc minute. So that gives you some idea of the depth of the survey. And right now we are in a time where we have 3 surveys in friendly competition: the kilodegree survey, the dark energy survey, and hypersuprime CAM, all following somewhat complementary strategies in terms of survey depth versus area. We're really building on the lessons from the first generation of, especially in that case, cosmic shear surveys, CFHDS, Cosmos, and the Blend survey that carried out initial cosmic shear measurements of order 1 million galaxies or less. And right now we are dealing with 10 to 100 million galaxies. And this really is our bootcamp to get ready to interpret then the shapes and positions of tens of billions of galaxies that will come to our hard drives in the late 2020s from Euclid, the Nancy Grace Roman Space Telescope, and from Vera Rubin Observatory. These surveys want to constrain cosmology largely through observations of cosmic structure formation, where the main process is that gravity drives a structure formation, while dark energy, or whatever it is, slows it down. This is a measurement that's very complementary to the expansion rate, as this now probes the growth of fluctuations rather than the background evolution. On very large, close to linear scales, we can make progress with paper and pencil through perturbation theory. But if we want to describe cosmic structure formation into the nonlinear regime, we have to turn to numerical simulations, as shown in the example below, which shows you the evolution of the cosmic density contrast as a function of cosmic time. And for rough guidance, you could say that if you want to use perturbation theory only, it's probably safe to stick to scales similar to the BEO scale indicated by this white yardstick here. So if you imagine smoothing the field on these scales, you can see that one erases a lot of information. Now, if we turn to numerical simulations, that means we can predict the dark matter distribution for select dark energy models and maybe individual modified gravity models, but definitely not for all possible models at a time. So we need to be selective and really figure out how to stress test the lambda CDM model. The next problem then, though, is that, of course, the large-scale distribution of the dark matter density contrast is not directly observable. So we have to do some more work to connect theory and observations. Starting out from cosmological model and parameters, we can turn to simulation perturbation theory to predict the dark matter distribution or some summary statistics of it if we do perturbation theory. After that, all of astrophysics still has to happen to turn this dark matter distribution into the distribution of galaxies, light, and baryons. And then we still need a process to confront those predictions with observations that come in the form of galaxy positions, shapes, and colors. In the case of imaging surveys, CMB temperature and polarization, or other traces. Obviously, all of astrophysics has to happen is a big step, and a lot of the systematic effects I'm going to talk about today. I will pick a particular path for this comparison of theory and observations, in that I will focus exclusively on summary statistics. So I'll talk about analyses that then condense these catalogs of billions of galaxies into measurements of the two-point correlation function, counting clusters, the largest peaks in the distribution, or more experimentally characterizing the most extreme underdensities, or later on potentially also three-point correlation functions. There are other approaches doing this comparison at the field level, but summary statistics so far are the workhorse of these cosmology analyses. So our most standard measurement then is the two-point correlation function, which measures the axis probability of finding galaxy pairs as a function of separation. And if we know distances to galaxies and assume a relation between galaxy density and dark matter density, that is galaxy bias, then this galaxy two-point correlation function is nicely related to the matter power spectrum, a quantity where we can then easily connect to theorists. Shown here as a function of wave mode k. On very large spacer scales, we have a simple change in amplitude going from redshift 3 to redshift 1 to today. That's linear growth, which we can predict with paper and pencil, or maybe simple numerical integration. Then at somewhat smaller spatial scales, we first have the imprint of the baryonic acoustic oscillations, or standard ruler. And further to the right, at the small spatial scales, is the onset of nonlinear structure. All imprinted in the galaxy two-point correlation function. The next tracer that I wanted to highlight is galaxy clusters, where we now want to characterize the largest bound structures in the universe, which can tell us something about the distribution of peaks in the initial density distribution, the rate of structure growth, and the evolution of volume elements. So for that, we have to identify overdensities galaxy clusters. In the case of optical surveys, that means we have to figure out which of these red galaxies here are spatially close to each other and belong to a cluster. Then we further need a relation between observed mass proxy, in this case, the number of galaxies, and the underlying halo mass, which then is something that we can relate to cosmology through this halo mass function. So that means we will have to put great efforts into characterizing this mass of the observable relation. Another measurement that we want to interpret is weak gravitational lensing of galaxies. So this is now the coherent distortion of galaxy shapes due to deflection by the tidal field of large-scale structure. The cartoon here on the right shows this exaggerated by about factor 100. They started out with circular background galaxies, and then calculate the shape distortion passing through the tidal field of the foreground distribution shown in yellow to red. And it's exaggerated that effect by a factor 100. With that, you can see individual galaxies aligning tangentially with these dark matter filaments. In reality, the effect is much weaker. Background galaxies are neither perfectly circular nor detected with such perfect delineation from the background. In reality, we are measuring the shapes of galaxies at a signal to noise of about 20. So this is a statistical measurement where we average over the shapes of hundreds of galaxies that are spatially close to average out their individual orientations and beat down the measurement noise in our estimates of this gravitational shear. So I've now talked about 3 different ways of measuring the growth of structure. That is galaxy clustering, weak lensing, and galaxy clusters. And as in the nice plot before, where I showed you the joint constraint from different measurements, wouldn't it be nice to also combine these different measurements? In the case of CMB, supernovae, and BEOs, that was easy to do. You can download the posterior from each of these experiments and multiply them yourself and experiment with the results, because these are uncorrelated experiments. However, when we now talk about combining structure growth traces, we basically have 3 different ways of measuring the same underlying matter density field. So our measurements are inherently correlated, and they may also be correlated to systematic effects. So instead of multiplying individual posteriors, we now have to embark on a joint analysis. Let me just give you a brief schematic. Each of these boxes here are work of probably tens of people in these large collaborations, so I can't do it full justice in this talk. But anyway, let me briefly explain the flow down. The first question we should ask is, what are our parameters of interest? For example, what type of model do we want to constrain? Are we looking at a simple dark energy model where we have sufficient numerical simulations to characterize the nonlinear regime, or some new modified gravity model where we only know about the linear regime? That will then inform which type of measurements and on which scales we can even attempt to model. So that then basically sets what our data vector is. We'll probably want some cosmology priors, which I don't need to go into today. The next more difficult ingredient is a likelihood function, where so far we typically assume that 2-point statistics are multivariate Gaussians, and number counts follow a Poisson distribution. That has worked sufficiently well so far, but improvements are clearly needed for future surveys. Then this likelihood function will allow us to confront our measured data with a model prediction. So that means we now need consistent modeling of all observables, including all our cosmology nuisance parameters. We'll likely also need a joint covariance. That is one of my specialities. Basically, we're talking about a large non-block diagonal matrix, including a bunch of integrals over the meta 4-point function. But I've learned that this doesn't really make for a good talk topic. So ask me afterwards if you really want to. And then the astrophysically most interesting part, I think, are the systematics parameters. So I call here systematics or nuisance everything that is not our cosmology parameter on the left-hand side of the equation. One definite statement about these systematics is that they will vastly outnumber our cosmology parameters. So we need to be systematic about parameterizing and prioritizing them. We will also need priors on these systematics that we can hope to validate using external data and simulations. Okay, let's get into precision cosmology analysis. There's often this talk about precision cosmology being the next frontier. where precision simply means, yes, we have succeeded in getting a bunch of big surveys that will deliver billions of galaxies and high precision measurements of the CMB very soon. And if we are complacent and apply the same analysis today, then precision really just means that our error bars shrink because the statistics of the experiment get better. But there is no guarantee that our analysis will tell something about the true parameters of the universe. So in addition to precision, we also need accuracy, so that hopefully we will be able to accurately measure cosmology parameters with small error bars. The problem, though, is that accuracy typically comes at the cost of complex analyses. Okay, so as a warm-up, let me tell you about a simple exercise in astrophysical systematics, which really wants to showcase that precision cosmology means that we are person power limited and creativity limited. Because in the first pass, it's easy to come up with a very large list of systematics nuisance parameters. I did that exercise in the dark energy survey before we had data. And I list here some of the main parameters that people came up with. They are the standard ones: galaxy bias, the cluster mass observable relation, and a bunch of cosmic shear measurement uncertainties. But the important point is that when we first did this exercise, people came up with a list of 500 to 1,000 parameters. And I told you on slide 1 that we are after about 6 parameters characterizing the lambda CDM model. So that's not a good situation to be in. One could try to self-calibrate and marginalize all these suggestions, but it would be costly, both computationally and in terms of constraining power. So we'll need to be systematic about systematics. And let me show you that in a cartoon. First, we'll start out with a series Dreamland. That is a systematics free survey, where we can also afterwards reassure ourselves that we actually recovered the correct parameters. So we get a bias-free parameter estimate with statistical uncertainty. Then in the next step, if there is some ignored systematic effect in the analysis, our parameter estimate would be biased. But because we are still in this ideal situation where we realize the bias, we can just think and figure out what's going on, put in a model for the systematic, and marginalize over the corresponding parameters. So at that point, we remove the parameter bias, but increase the uncertainty in our measurement. We can now go through this exercise for a bunch of different systematics and figure out which ones are most hurtful. So that's where we'll probably want to put in extra work. And by that, I mean that we want to look at external data and improve the priors on the corresponding nuisance parameters. So that then after including these priors, we can recapture some of the information that had been lost before. Of course, in reality, the world won't be perfect. And most likely, many of our systematics mitigations will end up with some residual parameter bias and increased uncertainty. And I will next tell you how we can use different cosmological measurements to understand in what regime of this residual uncertainty we are, and use it as an important cross-check. So with that, let me come to my first real-world example of navigating complex systematic spaces. That is the year 3 analysis of the dark energy survey, where we analyzed about 100 million galaxies. Again, as a reminder, this is a warm-up to the tens of billions of galaxies that we'll have to make sense of with Rubin Observatory. So in this analysis, we used 2 different cosmic tracers. First of all, we probed the late-time meta-density distribution using about 10 million galaxies with accurate redshifts. So these are relatively bright galaxies, which we then split in 6 photometric redshift bins. And in each of these bins along the line of sight, we measure their clustering. That is now the galaxy 2-point correlation function. We also have 100 million galaxies for which we measure shapes. This fainter sample has poorer redshift accuracy, so we only split it into 4 tomographic bins. And from this weak lensing survey, we measure the correlation of galaxy shapes, that is cosmic shear, and also the cross correlation between lensing and galaxy clustering, that is galaxy lensing. This basically then allows us to weigh the halos hosting our lens galaxies. This analysis is the work of a large collaboration, and it actually had been in the work for 4 years following on the year 1 analysis with over 150 active participants, allowing us to go from pixels to cosmology in about 30 papers. This required algorithmic and modeling improvements in all analysis stages. And I'll defer to this nice flowchart here from Alex Amon, showing you how we go from the data on the left-hand side in terms of wide field images and deep field photometry to eventual cosmology constraints. So this includes, for example, enormous improvement in the modeling of the point spread function and shear measurement null tests, as well as quite a breakthrough in image simulation required to calibrate how well we do our weak lensing measurements, and a bunch of other improvements along the way. On the topic of systematics, we ended up with 26 different systematic parameters, describing the galaxy bias in terms of 1 linear bias parameter per redshift bin, magnification bias, again in the simplest possible parameterization, intrinsic alignments, the effect that the intrinsic shapes of our background galaxies are not randomly oriented, which poses a problem in averaging out the orientation in the cosmic shear measurement, but that we put in a perturbative model, and then additional simple calibration parameters regarding the redshift distributions and shear measurement. This list, of course, then is known to be incomplete. And there are known systematic effects that we don't include. For example, we know that there's baryons in the universe, but we model the matter distribution based on dark matter only simulations. So we deal with this incompleteness by removing data points believed to be contaminated. That means we throw out most of the signal to noise. And we also have to stress test that our simple parameterization is sufficiently flexible given the accuracy of our, the statistical uncertainty of our measurement. After going through extensive validation, we arrive at these results, where the blue contours show you constraints on the matter density and clustering amplitude from cosmic shear alone. And the orange contours show the same constraints now from clustering and galaxy-galaxy lensing. Both of these are marginalized over 4 cosmology parameters and their respective nuisance parameters. As these 2 splits of our data are consistent in the full parameter space, we conclude that our systematics modeling is sufficient, and we are allowed to combine them into the black joint constraints. So that is our main DES result. Of course, the big question then is, what do we learn in terms of stress testing the lambda CDM model? So for that, we now compare DES, shown again in black, to results from cosmic microwave background, shown in green, and also other measurements of the matter density and clustering amplitude at low redshift. That is supernovae, BEO, and redshift space distortions. We can combine DES and these results shown here in orange, which all probe late universe physics, into the joint purple constraint. From that, we conclude that within our current error bars, these low redshift probes are consistent with the CMB results at about 0.9 sigma or P of 0.34. That's the current snapshot. To make progress in the future, we want to observe more galaxies, combine more probes, and achieve better systematics control. So let me go through these in turn. One analysis that I want to highlight beyond the combination of weak lensing and galaxy clustering is a recent paper led by grad student Chunhao Tu, where we obtained cluster cosmology constraints from cluster number counts and large-scale two-point statistics. So we extend this 3x 2-point analysis of cosmic shear, galaxy-galaxy lensing, and galaxy clustering to include cluster clustering, cluster cross-galaxy clustering, large-scale cluster lensing, and cluster number counts. That means we calibrate the cluster mass-observer relation entirely through large-scale clustering, not a small-scale weak lensing, which makes it much easier to account for selection biases. In the end, we find cosmology constraints that are consistent with other DES probes. The important point here is that this analysis now allows us to consistently include the constraining power from number counts, which is a qualitatively different probe than the various two-point statistics. So what I'm showing here is our complete result from this analysis shown in red, versus one that excludes number counts. So this would shows how much information we gain over the 3x 2-point analysis by including galaxy clusters just as another tracer of the meta density field. And you can see that most of the gain here really is from including the cluster mass function that has very different degeneracies. So this means this can unlock a substantial gain if we can accurately calibrate the mass-observer relation. And the small plot on the bottom right also highlights expected gains for Rubin LSST joint probes. Again, showing now from green to black, the information gain expected from including the cluster mass function with self-calibration of cluster masses from Rubin data. So this would be quite a substantial gain in terms of our possible constraints on the dark energy equation of state. Now, in terms of systematic opportunities, I'd like to highlight here this rogue DES analysis by Anthony Lewis, repeating our year one analysis shown in gray, once fixing all systematic parameters to their best fit values, shown in red. So this illustrates the potential gain if current systematic models could be entirely constrained from external data, if we could get perfect priors on all the systematic effects. Then in the blue contours, he also removed the scale cuts. That is, he included all the signal to noise that we threw out due to modeling uncertainties. That is now a very optimistic view, because modeling these scales requires new systematic parameters. But I hope it highlights that there is still a tremendous opportunity space within this data set. As one example, let's talk about the impact of baryons on the distribution of matter, which is the leading uncertainty or astrophysical effect limiting our cosmological interpretation of weak lensing. This plot here shows all the weak lens cosmic shear measurements from DES, and the data points in the gray background with the gray shaded background are those that are excluded because of modeling uncertainties due to baryonic effects. Our postdoc Hong Jin Huan now reanalyzed this data, including all measurements down to 2.5 arc minutes, so including all the data points on this plot. For that, she had to come up with a model for baryonic effects on the weak lensing statistics, which are characterized here in terms of the effect on the power spectrum, shown as the ratio of the power spectrum measured in hydro simulations compared to a rerun of the same simulation using gravity only. And you can see that this leads to a substantial modulation of the meta power spectrum with effects of up to close to 40%. She then built a principal component analysis based on the different simulations, basically enveloping the possible effect based on all the models that people had simulated so far. Incorporating that into simulations, into our analysis is then shown here, where the orange contour shows the baseline analysis with the conservative scale cut. The green contour includes all the scales, but does not model baryons. So don't do that. That is known to lead to biased results, and only is supposed to show the possible gain of constraining power if we could really figure out how to describe baryons with very few nuisance parameters. The blue contours include all scales and very conservative modeling of baryonic effects. So at that point, we don't gain very much. However, we already know that some of the existing hydro simulations have been ruled out by other observations. Say the original illustrious model, where we know that the X-ray measurements don't compare well to observations. So now putting a somewhat informative prior on our baryon analysis based on certain simulations being ruled out, we can regain some of this constraining power shown here in the gray contours. So at this point, with some limited external knowledge about what baryonic models are ruled out, we can improve our constraining power by about 20%. And of course, there's much room for improvement using observations at other wavelengths to further shrink these error bars. We can also, of course, turn the situation around because the boundary between nuisance parameters and parameters of interest or cosmology parameters is completely arbitrary. They're all just parameters in a Bayesian analysis, and we decide what to marginalize. So we can turn that around into constraints on baryonic feedback effects, shown here in terms of our principal component strength Q1. And to interpret that number, the vertical lines show you where the different hydro simulations with different prescriptions for baryonic feedback fall in this parameter space. And then the posteriors show constraints on baryonic feedback from DES alone or DES plus Planck, showing how both of these data prefer moderate feedback strengths. Basically, incompatible with the Cosmo-Alts AGN scenario with the highest AGN temperature. And that makes a lot of sense. So this all looks nice and is a first step forward to recapturing the information imprinted in small scale weak lensing. Okay, instead, let's turn towards the future, which is starting very soon. For example, Reuben Observatory had engineering first flight already, and commissioning is about to start. So we better get ready for science analyses. I briefly want to highlight here the science requirements document, which is starting to realistically characterize the systematics parameter space that we expect for these analyses. This is available on the archive and importantly includes links to all the data products and Fisher matrices that you can use for variations and your own forecasts. These are the first joint forecasts by the science collaboration since the initial LC science book in 2009. So this is based on a much more mature survey and analysis modeling, including the understanding of systematics. And here we had considered two classes of systematics. Those that are self-calibrated from the data, that is galaxy bias, intrinsic alignment, and the cluster mass observer relation. And those that are externally calibrated, we basically put constraining priors on photo-Z uncertainties, shear calibration, and photometric calibration. And the part on the right just shows you our predictions for equation of state parameter constraints from LST year 10. My important point, though, is that systematics really start to matter a lot in this scenario, meaning that survey optimization or also observing strategy optimization is getting much more complicated. Before, in the first approximation, one could say that more galaxies is always better And higher number density of galaxies is really good because it suppresses shot noise or shape noise. In a 2D parameter space, we basically then have to balance survey area versus number density of galaxies. And especially if we're looking at late time phenomena, such as dark energy, going far beyond latitude 1 doesn't buy us very much. Meaning typically it's then useful to prioritize area over number density, if you have to pick one. However, this view of survey optimization concerns statistical error bars only. And to make real progress, we have to consider how well we do in terms of systematics control. Let me just give you one example how important this is, namely galaxy bias. So that's the relation between a galaxy population and the meta distribution. If initially we think that we can only model the large-scale distribution of halos hosting these galaxies, then we arrive at constraints illustrated by the black, red, and blue contours here for an LSST Wiglensing plus clustering analysis. And if we additionally think that we can also model the clustering of galaxies within halos, illustrated in green here, which comes at the cost of a bunch of additional systematic uncertainties, which we at least partly include in this analysis, we arrived at these green contours. So that is an improvement in figure of merit by about a factor of 4, which would correspond to a almost F sky equals 2 survey for large scales only. And I'd argue that obtaining 2 independent skies is far more futuristic than accurately modeling the small scale galaxy distribution. So this is definitely an area of optimization for future analyses. This is just one of many of the examples. In practice, I think survey optimization has to include not only the number density of galaxies and survey area, but consider the main systematic uncertainties in this process. That's a complex space. One thing that unfortunately is clear that each of these optimizations will be costly. So we have to use some physics intuition and be strategic about which of these to investigate beforehand, also guided by results from previous surveys. One optimization process that I'd like to highlight here is potential synergies between Rubin and Roman Space Telescope. So in a standard view, the Roman Space Telescope will constrain cosmology through a supernovae survey, providing wide, medium, and deep imaging, and the high latitude survey, having both a spectroscopic and imaging component to do spectroscopic clustering and Wiglensing. Importantly, though, the observing strategy is not yet defined, and I will take into consideration community input. So on the right-hand side is one possible realization of the Roman observing timeline, showing in different colors the different observing programs. And red here is the imaging component of the high latitude survey. We have gone through very detailed forecasts of the performance of the baseline high latitude survey on Roman Space Telescope, where I don't want to bore you with the details here. But basically after marginalizing over more than 80 systematic parameters in a full simulated likelihood analysis, we combine cosmic shear, galaxy-galaxy lensing, galaxy clustering in a photometric and spectroscopic survey, cluster number counts, cluster Wiglensing in supernovae 1A to arrive at certain predictions for how well the baseline survey will do. More interestingly, what I want to highlight here, though, is the potential for a hypothetical wide survey. Roman also has a W-band filter, which you can basically think of as a light bucket, which means that we can cover a large area with space quality imaging in a short amount of time. Especially within just half a year, we can reach 95% completeness for the LSST lensing sample down to a limiting magnitude of I of 25.3. And within 1 year, we could do the same for full sky. Of course, W-band based lensing may be subject to some systematics we haven't considered yet. But the main idea is that we combine space-based imaging with the W-band with the Rubin survey, providing photoses for the entire sample, and compare that to the reference survey. So in blue here, we show the constraints on the dark energy equation of state from the high latitude reference survey as currently defined. The red contours show the standard LST year 10 contour constraints from clustering and relensing. And in black, we show the combination of this hypothetical white band imaging with Roman combined with the Rubin's galaxy sample for photometric redshifts. Importantly, this would amount to a factor 2.4 increase in figure of merit over the case of Rubin only. So that again is a substantial improvement. If such a wide band survey with Roman could gain traction. And while there are many more synergies across different surveys that allow us to calibrate different systematics, let me just conclude here by saying that we are entering the decade of very large galaxy surveys. And as I hope I've shown, most cosmological constraints from these will be systematics limited. This means that we will absolutely rely on accurate systematic expressions and priors. As I've shown, the different probes and analysis methods enable accurate cosmology by first helping us identify and understand systematic effects, and then after that is done, allowing us to maximize constraining power. Importantly though, this plan requires collaboration across different surveys and wavelengths, and for different collaborations to collaborate on analysis frames early on. Thank you.
Great. Thank you very much, Elisabeth, for extensive overview of the status and challenges of the Very Large Galaxy Survey. So we have time for questions. Please feel free to raise your hand. Meg has a hand up.
Hey, yeah, thank you very much. That was really a complete and masterful description of all of the incredible machinery needed to analyze these huge surveys. And you haven't even begun, as you said, because the big ones are really coming. I had a stray thought for the shear measurement. You need to know something about, or you would like to know something about the intrinsic shapes of galaxies. And of course, there's a systematic difference between what disk galaxies look like and bulge-dominated galaxies. If you had an accurate way of determining that, which with high resolution imaging you have, so even HSC data are probably good enough, but certainly Euclid and Rubin Roman data should be very much good enough. If you had some kind of just blunt force classifier that would tell you what every galaxy in the sky was, what its bulge to disk ratio was or something, then you could have different assumptions, different underlying distributions for each, and redo your shear measurement. Do you have any sense if that would make a difference, whether that's contributing any kind of uncertainty?
That's a very interesting question. I think the first limiting case that I look at here is disk galaxies, where basically then the effect of shear, or at least a shear component along the major axis, is completely degenerate with inclination. So that would, I think, make it difficult to recapture information just from knowing it's a disk galaxy. If we get external information, say from the Tully-Fisher relation, learning the inclination, then yes, that would help tremendously.
But I thought you'd do this sorry, I'm not super familiar with since you're assuming a sort of random orientation, random inclination angles, don't you take that out?
I mean, yes, we average it out by averaging over many galaxies. If we wanted to improve our constraints based on the additional information that a galaxy is a disk, then I think we would need some prior on inclination, because otherwise that is completely degenerate with shear, and I don't see how just saying it is a disk but randomly inclined would allow us to improve the constraint on shear.
Okay, I mean, it seems to me if you put a bucket of disk galaxies which have random orientations and then a bucket of round galaxies, then you have very different, I mean, and yet the mass, the lensing has to be the same for both buckets. So you have a sort of independent, anyway, I'm sure people have thought about this more than I. Thank you very much. Really enjoyed your talk.
Okay, we have hands up from Krause.
Yeah, thank you very much for the very nice talk and overview of the field and where it's going. I was wondering, because your talk dealt quite a lot about the systematics and how to deal with them. To properly incorporate all the different correlations between different systematics, you need a full joint combined covariance matrix, which includes all of them. And you're doing cosmological analysis on this. So you need to have the baryonic feedback effects for different omega matter sigma 8 and take the covariance of the whole thing. And just taking a covariance matrix of all the baryonic effects and bias and everything in a single cosmology is hard enough, doing many realizations and all that. So how do you really capture all of that into a single covariance matrix?
So in the approach that I described here, we are trying to avoid putting in just a large systematics covariance, because that means at that point we have already analytically marginalized basically and erase the chance to self-calibrate from the data. You can either put your systematic in the covariance, just say, okay, this definitely just assume it's prior dominated, then that's a fine approach. But if you have a chance of learning something from the data, then I think putting it just dealing with it by putting it in the covariance is conservative, as it erases that constraining power. So I think, especially for baryons, it makes more sense of trying to think of a predictive parametric model, say the impact of baryons on the matter power spectrum, which then in future iterations needs to be a function not only of our baryon model, but also of cosmology. So far, people often have assumed that the relative impact of baryons is fairly independent of cosmology, at least in the one Hale regime. But of course, that's something that we need to absolutely revisit for future analyses.
Okay, thank you.
Okay, are there any other questions for Elisabeth? Maybe I'll ask one question. You mentioned about the baryonic effect, and do you have a sense of how much of that is a problem for the sigma 8 or S8 tension that people have been talking about? I think there are some claims that maybe baryonic effect does not explain everything. In your sense, how important do you think are the baryonic effects, which really needs to be modeled out? And there's a road ahead for that. But to what extent is that a problem? Another question is, you also talked about the self-calibration idea when you were presenting the LSST forecast. Can you use self-calibration now to sort of self-calibrate the baryonic effects in the present-day data? And to what extent would that self-calibration idea would work for the future data?
Okay, two parts. This is, I think, my response to the self-calibration in current data, but I guess let's first go back to how much baryons matter in current analyses. And there I will mostly focus on the dark energy survey because I was responsible for throwing out all the signature noise, determining rather conservative scale cuts. So what we've done to hope that our analyses are robust to baryons is that we take the full meta power spectrum, including baryons, from hydro simulations. In this case, Cosmo Owls with the highest AGN temperature, so a rather extreme baryon model. Use that to predict what our observable statistics in terms of psi plus minus, the cosmic shear correlation functions would look like. And then compare that to the same statistics predicted from dark matter only, and make sure that we throw out all the scales where the difference between these two different models is significant. So of course that relies on having this reference model, and the key is in choosing a conservative reference model. And I would hope that Cosmo Owls 8.7 is on the conservative side of how strong feedback could be. So if that's true, then I think the DES constraints are robust to baryonic feedback. I must admit that I'm not quite as familiar with the procedures of HSC in kids. They've chosen somewhat different approaches. I think in the kids' case of marginalizing it all through HM code, which is a different choice and something that we could debate offline.
Sure.
Then back to the self-calibration idea. So these posteriors now on the baryonic modeling basically are entirely due to self-calibration. By saying if we just treat this as one of the many new parameters in our MCMC, and then just look at the marginalized posterior on the baryon parameter, showing you that definitely we are starting to self-calibrate feedback. And especially when we include here DES plus Planck, where we intentionally chose only EE plus low E, because in that case, DES and Planck agree perfectly, so that we don't have any internal tension between DES and Planck that would then somehow project into baryon constraints. So basically these two curves show you how the self-constraining power increases as you increase the overall constraining power of your data set.
Wonderful. Yeah, thank you. Thank you for answering my questions. And I certainly would actually like to follow up on some of the discussions about these issues of various other surveys. But I'd like to take a moment. Actually, maybe we're sort of hitting the end of the hour. So let's stop here for the day. And so let's take a moment to thank Elisabeth. Thank you very much for your great talk. And I hope that you can actually visit us in person sometime in the future.
I very much hope so. Thank you for showing up today. Goodbye.
Thank you. Bye-bye.